on yet another summer day. When is it going to stop being summer? Does anyone know? Because I'm really tired of being hot all the time. This weekend?
Technically, this one. Oh, I don't know what.
Oh, it's just going to magically.
Like 70s, like after the rainstorm.
See, now that's what I'm talking about. Yes.
What's the record for today, though? The record for this date in Lawrence is 96 degrees.
Ugh.
And it's expected to be 95, according to my app. So.
That's terrible. Yes.
For September 19th.
That's tragedy.
I think the old record set 1953. That's what I did this morning.
That's what you learned this morning. Thank you for sharing. Yes. Good. Well, here's what other people may have done this morning, right? Our quiz. So should have finished this by now. Once again, you get points just for trying, and I look at your answers to see if there's any common misconceptions or other things that will be useful diagnostically for me. But we can go through this. You should have the answers available to you if you were to look this up. There we go. Make it a little bit bigger. So briefly then, 3 kinds of parameters in a measurement model. Those are item things: intercepts, loading/slopes, and residual variances. So the intercept is the expected item response when your factor is 0. The loading is the change in the expected item response for a 1-unit change in the factor. And then the error variance is anything left over in the item that's not the factor, not the mama. Number 2, structural parameters. These are factor things: factor means, variances, and covariances. They are either going to be set to known values for identification or estimated. So that's the other trick of identification there. And the last 2 we talked about just on Monday, so this is relatively recent: degrees of freedom. So it's all relative to data going in and estimates coming back out. So data going in, item means, item variances, and all possible covariances. There's a formula by which you can calculate how much that is. It's number of variables times number of variables plus 1 over 2 plus number of variables. Once you get enough practice, you can just say that off the top of your head too, I promise. And so then the question is, did you spend as many parameters as you could have, or more or less? So if you tried to estimate more parameters than you had pieces of data with which to estimate them, that's bad. That's under-identified. Not solvable, not testable. You will get an error message instead of answers when you try this. And the error message will say your model is not identified. That's what it will say. If you estimated as many parameters as you could have, you used all of them, just identified, then the model can be estimated. You will get your numbers back, but it will fit perfectly because there's no room to be wrong if you spent every possible degree of freedom. And then if you did not estimate as many things as you could have, fewer parameters than data points going in, that's over-identified, and that's where we want to be. So then that leads into the last question then. Estimable means that you can find numbers. Testable means that you have positive degrees of freedom. So how many items do you need for a model to be estimable? 3. How many for it to be testable? 4. How many did I recommend you have at a minimum last time? I said at least 5 so that you have some room for something to not work. If you have 2 items, then what? Can't do it because it's under-identified unless you do what? What's the catch?
You have 2 items for 1 factor within 1 factor.
Nope. Within just 2 items on a factor. I thought I heard someone say it. We make the loadings equal to each other. Because the problem is that there's only 1 covariance and you're trying to get 2 loadings to predict it. So if you make the 2 loadings the same number, then you're estimating as many parameters as you have pieces of data, and you're just identified. So putting a factor over 2 items is mathematically the same thing as just letting them be correlated. That's all you're doing. You're taking the correlation between the items and putting it in a circle and giving it a name. Questions on that? No? Okie dokie. Then I will take a look at those later. In terms of our agenda, I made the executive decision to move your homework back because I don't want to feel like I'm rushing through it to get to it. So your homework 2 is due a week after I originally said. It'll be due on October 5th. So that'll make sure that we have plenty of time to cover this stuff and for you to feel comfortable with it. There'll be no homework the week following, and then homework 3 will be due 2 weeks after that. So homework 2 is going to be using CAN data to get you practice using Mplus and fitting these models where you know what the right answer is supposed to be. Homework 3 is going to be your chance to estimate CFA models on your own data. So if you haven't figured out exactly what data you're using, if you haven't gotten it all cleaned up and situated so that you can actually do something with it, now would be a great time to work on that while you don't have a homework that is currently due. All right. So let's pick up back in Mr. Lecture here. Where do I want to start? We did estimation, and I felt like that was the point where most of you started looking like you were either afraid or bored or just otherwise like, make it stop. And even playing Skilo didn't help. So I thought, what can I do to help? And I remembered making this for another class, and so this is what I sent to you yesterday. So I want to go over this because I think it may help demystify exactly what is going on in the world of maximum likelihood. Where do the numbers come from? So I have several different distributions here. Let's go to the normal tab, which is the first one. I'm going to reduce some of these decimals here so it's not quite so busy. And there we go. So I have made up data. 10 observations, each with a different value from 1 to 10. And what I'm going to do is calculate the model log likelihood from fitting an empty model to these data, meaning just estimating the mean of these observations and their variance. Now, I don't have to estimate their mean and their variance. There's formulas for that, right? How do you compute a mean? You add them up and divide by the number total, right? How do you compute a variance? Yep. Sum the difference from the mean, square it, divide by the number of items, right? Does that sound right? Something like that, right? Well, it turns out that the only reason there are formulas for that is because of the use of the normal distribution. So in your Enders chapters that I gave you on your reading list, he has the clearest depiction of how maximum likelihood works that I've ever read. And he shows basically how the formulas for maximum likelihood simplify into those easier formulas in the case of normal. But I want to show you how you get a likelihood out of those ideas. So I calculated the mean. Here's my formula, average of those numbers. And I calculated the variance of them too. So I know what the answers are. So what I'm doing here to find each observation's height, and I don't know how to make the formula up here bigger, but I'm using the formula normdist in Excel. It returns the height of that value on a distribution where you specify what the mean and the variance of that distribution are. And so I did that for all 10 of my observations. Now you note that these numbers, these likelihoods, are very small numbers. They're very close to 0. If you take the natural log of them, that's the next column. And Excel, it's ln instead of log. Log is log base 10. And that is this blue line right here. That is the height, given the right mean and the right variance for those 10 observations of each observation. Not coincidentally, observations that are closer to the mean have a higher height. They're taller. They're more likely to have come from a distribution with that mean. The sum of those log heights across all of these observations then is right here. And that's my index of how likely this entire set of data is, given that mean and that variance. Yes, sir? Yes, although you can't say probability, but you can hang on to that as an idea. Its probability is only correct if it's a discrete distribution, whereas this is a continuous distribution, so the probability of any exact point is undetermined, but likelihood is the idea of probability in this space. So yeah, it's the height. So the normal distribution pictures then, let me find those, we looked at those last time, just reminding you what this is. It's the height. It's the location on the y-axis for any given point under one of those humps. So what happens then if we get the answer wrong? Well, what if I think the mean is a little bit different? I just try a different number from 5.5. I calculate the height now under a different distribution. If the mean were 5.2 instead of 5.5, that means the variance is going to be different also. Actually, I just put in a different variance for demonstration purposes. Now here's the height under that distribution, and that distribution is shown in red. So the middle is moved over a little bit, and you'll note that it falls off much more quickly, because if I say the variance is 2 around a mean of 5.2, these observations far away from the mean are very unlikely. So that what we're trying to do is find the most likely height for everybody at the same time. So even though red wins for the people in the middle, blue wins for the people on the outside. So somewhere in here is like purple, right? You need to find the one that everybody wins simultaneously. And it's easy to show this in the univariate case because there's only two things that go into this normal distribution formula, the mean and the variance. But if you were to take these data and read them into SAS or read them into Mplus and just ask it to estimate the mean and the variance, this is the number that it would give you back. That's the log likelihood of the right answer. So it's literally just the sum of the heights across all your data points, where in what we're doing, each person has a bunch of items. So it's a multivariate height because it's characterizing the likelihood of their 6 items or 8 items or however many to have simultaneously. But it's one number that characterizes that height for them. And that height for each person gets added together to create the overall height for the model. So you'll notice that you can't look at the height, this minus 24, and have that mean anything. These numbers have no absolute meaning. They only have relative meaning. So if we look at what the answer is over here in red, if I put in the wrong mean and the wrong variance, this number is smaller. So the model estimates that you're coming up with are the ones that give you the relatively best height for that model. That's how it decides which answers are the right ones. Like in this case, that's how it decides to keep the mean of 5.5 instead of the mean of 5.2 and the variance of whatever it is instead of the variance of 2. And this is a normal distribution, but you can do it for, on the next tab, here's what it would be if you have binary data. Here's what it would be if you have binomial data and the binomial log likelihood. So each of these heights is tied to the particular formula that you used, and the formula is the distribution it came from. So when we say we are assuming things are normal, what we're saying is we're assuming it's normal, meaning that normal is the formula we're using to calculate height. If normal isn't plausible, then the normal formula to calculate height with is maybe not a good representation. Maybe it should be something else. The good news is that there are solutions using maximum likelihood paired with almost any distribution you can think of. There's a million kinds of distributions out there. Our task is just to figure out which one is going to be a reasonable enough approximation for what the outcomes look like. So, does this help at all? Maybe. It's just height. The idea is that you fill in guesses for all of the model parameters, That gives you a prediction. You then calculate the multivariate height for that prediction for each person, add it up, that's the model. It goes through this process trying different versions of those answers until it comes up with the relatively best possible height, the tallest, most likely, across all the people. So then we compare our relatively best height to alternative models that are going to be either better or worse. And that's where we left off yesterday. Or yesterday, whatever day that was. Last time, how's that? So let me, I'm not going to do this yet. Yeah. Let me jump ahead a couple slides and then come back, because I think we're ready for this sort of part right here. So I'm starting on slide 43. And I'm going to get paint out, because I saw a comment posted on my YouTube channel thanking me for using paint instead of the chalkboard so they can follow along. Some random person on the other side of the world who's also in our class, did you know that? Said, okay, I like paint. Get out paint. Get ready for that. So slide 43 then, the big picture of fit. So the things that the model has to find when it's being estimated are the parameters. So we have the mean per item going in, and the intercept comes back out. We have the variance per item going in, and what comes out is residual variance plus the contribution of the factor. So the loading dictates how much of the item is due to the factor versus error. It's the unstandardized loading squared times the factor variance. That gives you the factor part. And then E-variance, residual variance, picks up whatever is left to get back to the original item variance that we know in the data. So as long as each item gets its own residual variance, the item total variances are going to be perfectly predicted. So long as each item gets its own intercept, the item means are going to be perfectly predicted. That leaves us with one last source of data, which is the covariance among the items. Covariance is just a measure of association. It's like correlation, just in the units of the original variable. So we're keeping the original scales intact and trying to model the association. So we'll get two versions of a factor loading. The unstandardized factor loading, its job is to reproduce the covariance. The standardized factor loading, its job is to reproduce the correlation. So we can go back and forth from one to the other because the standardized solution just makes all the factor variances 1 and all the total item variances 1 so that you can interpret everything on a correlation metric. So as long as you have fewer loadings than you have possible covariances, then your model is estimable and testable, and that's where we have to worry about fit. So here's the spectrum of fit then. We've learned about 2 models so far, and this is going to be the 3rd. So the best possible model over here on the right side, good fit. This is known as the saturated model. It's labeled H1 in your output, and it's also the same as an unstructured covariance matrix if you're from my multi-level class. This is just the data. This is not a model in the sense that it's trying to predict anything. It's just trying to perfectly reproduce the data points going in. It literally estimates just the means, the variances, and the covariances. It doesn't try to predict them with any other kind of model parameter. So it is always going to be the best fit. This is the best you can possibly do, is just to let the data be what they are. Our job, the middle here, is to find the HO model, which is our factor model, 1 factor, 2 factor, etc., that can closely as possible approximate the best possible saturated model. So when we think about model comparisons, what we're going for is that our model is not worse. You can't beat the best, but you can come as close as possible to tying it. That's the idea. So when we drew on the board here, I'll draw with Mr. Paint. My y-axis here is going to be height. Here's my 3 models. So here is, this is the height from my saturated model. There's an S. And note that it is as tall as the y-axis. This is the tallest possible model you can have. Our goal is to get something that is as close as possible. H-O, H1. That's tricky. So this difference up here then is what we're interested in. This discrepancy in height, this difference in log likelihood height, that tells us if we did a good enough job. There's one more model that we will compare against that will show up against your output from the other direction. On the left side is what's known as the null model or the independence model. Now note that this model starts off looking the same as the factor model, it just has no factors in it. So each item still gets its own intercept. Each item still gets its own variance. In this case, it's not residual because nothing's predicting it, just variance. But it says no covariances whatsoever. So this is the worst possible model that you would logically entertain. And so that one, then, would be like this, something like that. Null model, N for null. There. I don't think I can type any more than that with the mouse. It's surprisingly tricky. So we're going to get various fit indices. Some of them are going to compare HO to null. Some of them are going to compare HO to H1. So we get absolute fit that has a p-value, and then we also get some other numbers that do not have p-values but give us some indication as to how well we did relative to these benchmarks. So here's an example of what the output's going to look like with these things, and we'll see this in just a minute. So we have, first off, number of free parameters. Now when I think free, I think leftover. Like that's what I think of, but no. That means free to not be 0. It means the number of parameters you used, number of things estimated. And in the example that we're working with, we have 6 items. So 18 comes from 6 intercepts, 6 error variances, and 6 loadings. So number of items times 3, if you have a single factor model, is the number of parameters being estimated. Next up is the log likelihood value for your model. Remember, you are the hoe. That number in isolation means nothing. It only has relative information when compared to either the best model or the worst model. So the best possible model is the H1. These other numbers I will come back to in just a minute. The idea, though, is that the difference between these two is what's meaningful. How far off is your model from the best one? And you want it to be not off. You want it to be as close as possible. So the next box, then, that's in blue here, it's reported as your chi-square test of model fit. This is the difference in height between your model and the best one. And unlike everything else in statistics, we want that p-value to be non-significant, not worse, not different. So in this case, the fact that it is significant to 4 decimal places means that we did not do a good enough job with our HO single factor model to perfectly recreate all the covariances. It's going to take more than just 6 loadings to recreate the 15 covariances among the 6 items. The last test here, chi-square tested model fit for the baseline model. That is comparing the saturated model to the null model, the best to the worst. So this one has nothing to do with what you said. This same number will show up just because of the data. Yes?
Okay. I have like a broader question about this.
Sure.
If we're comparing our model to the fully saturated model, which is perfect, I guess I just don't understand what we're doing. Like, how do we, like, if we have a perfect model that fits perfectly, why are we trying to create this other model and make it fit almost as good as our perfect model fit?
Good question. It's a very good question. There's 2 reasons. Number 1 is because we're trying to make evidence that these 6 items measure one thing. So that's why. It's like a proof of concept exercise in that sense. But then I am going to be interested in taking that one thing and seeing how it relates to other things. And so the latent trait, if this fits, if I have evidence that these 6 items do measure one thing, then relationships with other variables are going to be better characterized by that one thing than any of the 6 in isolation.
So what this is doing is, so basically you're removing the not the mama that's accounted for by the covariance and all forcing it to go onto, like you're not allowing items to covariate with each other, you're forcing them to load onto one big thing.
And the single thing is what gives the correlations then.
Yeah.
Yeah. So the only reason these items were related is because of mama. And we're differentiating mama from not the mama. And mama is going to go predict other stuff. And mama does it better than any of the 6 items would by themselves. Mama does it better, I thought. There's my take home for today. Does that help?
Yeah.
Okay. Yeah, this is the proof of concept part where it's like I have to demonstrate that I am in fact measuring one thing before I would take that one thing and look at relationships with other variables. Because if I'm wrong, if I'm actually measuring 2 things, then everything else I do is going to be wrong because I haven't characterized what's common in these items adequately enough. Okay. Other questions? Okay, so these numbers right here, the estimation procedure that we are using in Mplus, let me back up a little bit here, is what's known as robust maximum likelihood. So this is slide 40. So the formula that we're using to calculate height is the multivariate normal distribution. Because we picked that formula, that method of calculating height, we are assuming then that it fits the data. And in this case, the factors have a multivariate normal distribution, and so do the items. Now the question is, what if they don't? Because chances are your items don't have a perfectly normal distribution. So if they don't, this model may not fit. And it's problematic from 2 different perspectives. One is that a linear model doesn't ever shut off, so it could predict item responses that are impossible at certain levels of your trait. But then also, if the normal distribution doesn't accurately characterize your data, then all of these heights and the products of the height, like the standard errors and all of that, are going to be off. So then there's 3 possible fixes to non-normality that is not problematic enough to dump the normal, basically. Robust ML, which is what we're going to do. Transform the data, which is an option for skewed data that I will show you in a little bit, or just pick a whole different kind of model. So if there's no hope of a linear model working, that's where we would go to IRT or IFA. So any items that have boundaries, the most obvious case being binary items, but 3 category, 4 category, 5 category, anything with boundaries the linear model isn't going to work for. Something that is more continuous but isn't exactly normal would be a candidate for either transforming the data or robust ML. So Mayumi, this is you. Your data are not exactly normal, but they're continuous, and you checked the fit of a linear model and said it's not too implausible in what it predicts, so robust ML is going to save you. So what is this thing? And I believe it's chapter 5 in the Ender's book explains how robust ML works. But it basically checks for problematic kurtosis in your data, and it calculates an adjustment to the chi-square and to the standard errors based on how problematic your data are. So you end up with these extra numbers next to your log likelihood heights that are called scaling factors. 1 means your data are perfectly multivariate normal and you win. In that case, the robust ML becomes regular flavor ML. So we will use MLR, robust ML, for everything because it simplifies to regular ML if the corrections aren't needed, but it estimates the necessary corrections if they are needed. And I have never seen a scaling factor under 1 in my life. They are always over 1. You can interpret them roughly as the departure from normality. If you see anything above, like, I don't know, 2, that's the ones where it's like, this is impossible for these data. It's something that I sort of get used to looking at the numbers, but in the output that I showed you on page, this one here, page 45, the scaling factors are 1.4 for each of these models. So in computing the difference in height between your HO and the perfect H1, it adjusts those differences based on those scaling factors. So it's not a straight difference, and I will show you how to do that. In the spreadsheet that I put up for this example, let me get that out. I have a tab called MLR comparisons. And all of the likelihood ratio tests, or these comparisons as they're called, for all of this example are in here. So this is a thing, by the way, that when MLR first came out, I used it in a paper like a month after it came out and totally didn't understand this whole scaling factor thing and computed the p-values and the chi-squares wrong. And then someone was nice enough to email me about it and let me know I was wrong. Like, well, thank you. But I redid the analysis, and the conclusion did not change, and so I said, hooray. So for instance, H1 here is the perfect model. So this spreadsheet is set up that direction matters. The model that has fewer parameters goes first. The model that has more parameters goes second. So the more, in this case, is the H1 perfect model. That was the the log likelihood that was given on the output, and the scaling factor that was given on the output, and the number of free parameters, meaning things that were estimated. That's the total number of item means, item variances, and item covariances. It works out to be 27. Our model, then, the one-factor model that we had started with in the example, its log likelihood is this, its scale factor was that, and it took 18 parameters because it estimated 6 intercepts, 6 residual variances, and 6 loadings. So all you have to do in using this spreadsheet is enter in that part. The log likelihood, the scaling factor, and the number of parameters, and then everything else is computed for you. Where the last 3 columns then, the scaled difference, that's your chi-square. So the 307, that's the test of how far off your HO model is from H1, so it is significantly worse. It's a chi-square of 307 with 9 degrees of freedom. So it's the difference in the number of parameters that we're looking at here. The saturated model has 9 more things estimated. And the exact p-value that comes from this chi-square is 0 to the 4th or 5th decimal place. So this is done for you in Mplus. You don't have to fit the saturated model. It's done for you. But that's what that comparison means. It's a test of absolute fit. It's the difference between your factor model, whatever it is, HO, versus H1. And H1 is always the same because that is just the data. The null model test down here, what this is actually asking is whether you have anything worth modeling. It's comparing a model that says you have no relationships among your items to a model that says you have perfect relationships among your items. If that test is non-significant, this one on the bottom here, it means you don't have any covariances worth modeling. Game over. The whole job of a latent factor is to predict the relationships among your items. If your items don't have any relationships, there's nothing for the factor to do. And it would make no sense to continue.
So that has to be significant.
It has to be, yeah. I've never seen it be not significant, but that would be the worst case scenario. All right. So let's talk a little more about fit. Slide 46, and then we'll look at the example. So there's 4 steps here. We'll get to maybe the first step today. Global fit, local fit, looking at the parameters and make sure they make sense, and then comes effect size, the idea of reliability and information per item. So step 1, global fit. That's what we just looked at. The chi-square is the index of the difference between your HO factor model and the H1 perfect model. You want your HO to be not worse, so significance is bad. It is very difficult to get a non-significant chi-square. It's dependent on sample size. As you can see from the formula up there, the difference, the FML, is multiplied by 2 times the sample size. So in very large samples, you will have a significant chi-square simply because you have a large sample. So people don't hold you to this standard very often, that you should have a non-significant chi-square. It happens very infrequently. For that reason, there are other indices of fit that also show up that are relative to either the saturated model, the best, or the null model. So here's a few more that you will see besides chi-square. Standardized root mean square residual. This is a number that indicates how far off, on average, the predicted correlation between the items are relative to the real ones. It's an average offness in a correlation metric. Here's a tip. In these names, any name for a fit index that has the word error or residual in it, you want to be little. You want to minimize error or residual. So a cutoff that's used, 0.08-ish or less, would be an indicator of a well-fitting model, that the average correlation is only off by 0.08. Another one that's very commonly used, RMSEA, root mean square error of approximation. That has the magic word error in it, so you want it to be small as well. So this is an index of how far off you are between the predicted covariance matrix and the real one in the data, scaled as a function of degrees of freedom. So RMSEA likes simpler models. The more stuff you have to add to the model to make the model fit better, the less happy RMSEA is going to be. This one, people use all kinds of labels for. I've given you a couple examples here that I found. Good, acceptable, eh. Some people think it should be 0.08. Some people it should be 0.05. Rather than getting into semantic distinctions with your labels, I just say the RMSEA was this, right? And let people call it whatever they want. There's some newer developments that I put on your reading list that I actually wasn't familiar with until just recently, that these fit indices, by the way, they're dependent on the number of variables in your model, as well as how related your items are. And so to the extent that not one size fits all, these numbers, the articles do a really good job of explaining the situations in which these numbers aren't going to apply, so I would encourage you to refer to those. And if you end up with a model that doesn't fit no matter what you do, look back at the articles and see if those conditions are the reasons. If you have a whole lot of items, for instance, you're going to have a really good RMSEA no matter what. If you have very few items, you won't. It works backwards for some of the other indices, like on the next page here. But the reason that RMSEA is very popular is that it provides you with another significance test, which is known as a test of close fit. So on the output, you will get a confidence interval, a 90% confidence interval around the RMSEA estimate, and you will get a p-value. And the p-value is that your RMSEA is less than or equal to 0.05. So it's referred to as close fit. But this is another one that's relative to the perfect model. These are all relative to saturated. On the other side, comparative or incremental fit indices, these are relative to the crappiest model, the null model, instead. And they have the word fit in them instead of the word error, and that means you want them to be big. So the CFI and the TLI basically do the same thing. They reflect the difference between your model relative to the null model. The CFI has an extra constraint that it can't go over 1, whereas the TLI does not. TLI is also known as NNFI, and for these you want it to be greater than about 0.95. And again, though, it depends on the size of your model as well as the effect size for your loadings as to whether or not that's a reasonable cutoff. But these are the traditional ones that are given. So let's take a look then, unless you have questions, thoughts, at what this looks like in real data. So back to example 4. So just to remind you, the backstory of this, 6 items thought to measure the same construct, which is forgiveness of situations. 3 of the items are written in a negative direction and were reverse coded, and 3 are written in a positive direction. Here is their correlation matrix. This is what the model is trying to reproduce, is this pattern of correlation. And I highlighted the potential problems that we're going to see in that the positive items are more related to each other and the negative items are more related to each other and less related in between the two. From these correlations and these variances, one can compute a covariance. Here's the formula for how you put those together. And so this is the answer key. This is what H1 is going to predict, the data, where the variances are on the diagonal and covariances are on the off diagonal. So covariances are hard to interpret because their size depends on the size of the variance. That's why correlations are almost always given instead, because they're easier to understand. But we are working with covariance in terms of what the factor solution is trying to predict. The standardized solution is going to predict the correlation matrix instead. But there's a one-to-one correspondence between the two. Here's the data. Not exactly normal, so we're using MLR for that. Do we need to go back over the first part of the code here to read in the data and such? Does anybody have questions on that? No? And then we went through different methods of identification. And because you all are starting to get that look again, it's time for a brief interlude. So last week, I told you about my experience waiting tables and singing to people on their birthday. And that was my analogy for different types of identification. It's like picking a key for a song. And I will give you my new favorite type of identification for happy birthday. My birthday was last Saturday, and my 3.5-year-old son made this for me. Yes, so happy birthday, Mommy. So this is much better than singing to other people, getting your own card. So that's my new favorite method of model identification right there. So yes, back to this story. Thank you, Huey. Yes, he'll be famous. He's on YouTube now. So this is what I'm going to ask you to do this way. This is the z-score factor method. That means fix the mean to 0, fix the variance to 1 for the factor. Estimate all the loadings, estimate all the intercepts, estimate all the residual variances. So just to review what the code is doing here, the stuff in green with the exclamation points, those are comments. So sit is what I named my factor. It's short for situation. I had to name it sit because you have to have 8 characters or less when you name things. Situation forgiveness is the idea. It's measured by these 6 items. The asterisk is not technically necessary except for the first one, but I put it here for completeness. It means each of these loadings is being estimated. When you put the variable names inside brackets, you are referring to their intercepts or means. Those are being estimated as well via the stars. And when you list the items by themselves outside of brackets, you are referring to either their variance or residual variance. So just to review the terminology, if a variable is an outcome, a dependent variable, an endogenous variable as it is known, meaning it is being predicted by something, you get intercepts and you get residual variances. It's an intercept because it is the expected outcome whenever the predictors are set to 0, and it's residual variance because it's left over after being predicted. It's what's left gets put out there. If you have a predictor variable, or what's known as exogenous, and I think of that as the x instead of the y, then you get means and variances because there's nothing predicting it to make it conditional. Mplus knows, based on the context of your model, which it needs to be. But they show up in different parts of the output under the name intercept, under the name mean, residual variance, or variance. So then these 3 lines then are my measurement model, item things, loadings, intercepts, and residual variances, respectively. Then we get to the structural model, which is my factor variance. I've fixed that to 1 for identification. And my factor mean, so the name of the latent variable in the brackets refers to its mean, and I fixed that to 0. So this model has 6 items for 1 factor. That means it is not only estimable, but it is testable as well. So here's my output. All Mplus is going to give you is the name of the factor, and then by, and then the list. It's up to you to recognize that these are factor loadings. So these are my slopes. So for instance, this first item, the slope is 1.234. Couldn't have made that up if I had tried. That means that for every 1 unit change in the factor, the outcome goes up by 1.2. So a 1 unit change in my factor is a standard deviation. So for every standard deviation higher in my factor, my predicted item response to number 1 goes up by 1.2. The mean of the factor is fixed to 0. That's what the 99s mean here. Then comes the intercepts. So item 1 has an intercept of 4.5. So this item is on a scale of 1 to 7. So that means at the average level of the factor, at a factor score of 0, the expected answer to item 1 is 4.5. Yep. For somebody who has a factor score of 0, they're at the mean for the average person, in terms of average in terms of their trait levels. The expected answer to item 1 is 4.5. For every unit higher factor, that expected answer of 4.5 goes up by the loading, 1.2. So if I round off here, a factor score of 0 at the mean gives me an expected outcome of 4.5. a factor score of 1 gives me an expected outcome of 5.7. And that's the kind of math that I'll make you do on your homework. Fairly straightforward. Now, riddle me this, folks. Can you have an answer of 4.5? No. It doesn't care. It's continuous, right? It's continuous and normal. So at 2 standard deviations, it would go from 5.7 to 6.9. And what happens at 3 standard deviations? It goes out of bounds. A linear model doesn't shut off. So in judging whether or not CFA is appropriate, that's the kind of thing you want to check for. It's not just about model fit. It's about the plausibility of a linear relationship between the factor and the outcome. Yep.
Even with continuous variable, there will always be a range within your data, or there are continuous variables, but there's only a possible range.
A truly continuous variable would be infinity.
Like, what about age? So let's say you study adolescents. Then within your data, there's a range between, I don't know, 12 to 21.
Yes, but you can picture what it would be like to be an 11-year-old or a 22-year-old. Whereas I can't have an answer of 8 on this scale. I think that's the difference. And age isn't usually a DV either. It's usually an IV.
But factors can be either. I think they're DVs.
Factors in this context are IVs because they're predicting the item response. They can be DVs with respect to other factors. Yeah, so right now factor is the predictor, is the IV. Other questions? All right, so then we get to the variance of the factor, which we fixed to 1. And then these are residual variance. So this is the not the mama. How much of item 1 is due to not the mama? Well, it's 1.5. To know how much that is, we have to know what the original item variance was. It was 3. So out of the total variance of 3, 1.5 of it is not the mama, which means 1.5 of it is the mama, is the factor. So half the variance in item 1 is predicted, is captured by this factor. So then here was an example of how the model makes predictions. So the first part, writing out the model, this is how the model generates the predicted item response for any level of a trait. We did that for item 1 to illustrate. In terms of reproducing the variances and covariances, the second part there shows how the original variance of item 1 gets recreated from the factor plus the residual. And the way it works is that it's the loading squared times the variance of the factor plus the residual variance. So we only need to know 2 of the 3 things here to figure out the third. And so that's why I describe the idea of each item getting its own residual variance as plugging the hole. Once you have decided on what the factor loading is going to be, the program has decided, I should say, and once you know what the original item variance was, which you know because that's in the data, the residual variance just has to become whatever the difference is. So you could solve to figure out what the residual variance is, given that you know the loading and that you know the total. So variances are always going to be perfectly reproduced so long as each item gets its own version to plug the hole. And then the covariances. So I have an example here with item 1 and 2. There's only one factor right now, so that simplifies things. The predicted covariance between item 1 and 2 is each of their loadings multiplied together and multiplied by the factor variance. So the model says that its covariance should be 0.866, However, it's wrong. In the data, the covariance is actually 0.577, so it's off. The question is it too far off, or is it close enough? So all of these numbers on this page are the unstandardized solution. Their job is to recreate the original item means, item variances, and item covariances. But we also can convert those covariances into correlations. And that's what the standardized solution then, that's how it is to be understood. It's in a correlation metric. So we get the exact same set of output, but now in a different, relative to a different reference point. In the standardized solution, all of the items have a total variance of 1, and the factors have a variance of 1 also. So the loadings then go from -1 to 1 as a possible scale. If you get negative loadings, something went wrong. So these loadings, 0.7, 0.5, those are how correlated the factor is with each of these items. We've adjusted for differences in scale to make these numbers as comparable as possible. So these numbers, you can say, item 1 is more related to the factor than item 2. I'm not doing a significance test, I'm just doing an eyeball test. But 0.7 is bigger than 0.5, that's what I know. You can pretty much disregard the standardized intercepts and the standardized residual variances. The only other thing on here that will be of interest is R square, which is each of these loadings squared. Because if standardized loadings are the R, the correlation of the factor with the item, then R square is that correlation squared. So 0.707 squared is 0.5. In other words, half of the variance in item 1 is due to the factor, and half is due to not the factor. And that jives with the numbers we saw on the previous page, where out of the total variance of 3, the residual variance was 1.5, which means the factor accounted for the other 1.5. So it's half and half. So either one of those is sufficient to think about effect size. Either you can report the standardized loading in a correlation metric, or you can report the R squares in an R squared metric. Take your pick. There's no hard and fast rules as to how little these can be. Like I said before, it makes me squishy to see anything under 0.3, because that's less than 10% factor and 90% something else. Like I said, there's no rules. Just that's my own convention. Yes.
So these are square values tied and these items measure
Mm-hmm. It means that most of the variance is attributable to variance in the factor.
So if really low, can we drop that item?
Yes and no. So we'll talk about this in a little while, I guess next time, but yes, if the loading is non-significant, yeah, I'd say the item goes. If you're looking to reduce the size of your scale, you would do so by getting rid of the lowest loadings. However, in a linear model, it doesn't pay attention to where the item is in terms of its difficulty, which also matters. So I wouldn't use this type of analysis for the purpose of making a short form. But yeah, generally speaking, fewer items means less reliability, but if you need to get rid of an item, the ones that are less related would be candidates to do so. Now, the other part of it is to make sure that you're looking at the wording and thinking about the idea of validity. Like if you have this item that doesn't tap into the same things that all the other items do, it may be less related because of that. But if you get rid of it, are you sort of narrowing your construct down more than you had wanted to? So it's, you know, it's an art and a science in terms of deciding what you need to keep. The only clear-cut case would be if the loading is non-significant, which means it literally isn't related and you don't need it. Okay. Other questions? All right, then. So then we do the same thing with the standardized solution. The standardized loadings multiplied together create the predicted correlation between these items, which is 0.36. The actual correlation was only 0.24, so it's off. And we can skip the rest of this because that's just for demonstration. And we get then to the page where there's fit. So this is page 6. So first question, degrees of freedom. Total parameters you could estimate, total degrees of freedom. That comes from your data. It's the number of items, V, times the number of items plus 1 divided by 2 plus V again. So for these 6 items, I have 6 times 7 divided by 2 plus 6 is 27. It works out to be 15 covariances, 6 means, and 6 variances. The model spent 18 of them. The model has 6 loadings, 6 intercepts, and 6 residual variances. It doesn't have any estimated factor means or variances because we fixed them to 0 and 1 for identification. Then we get down to the output that we looked at in the slides here, where I have additional notes. By the way, this is me being nice. Mplus does not help you understand this. This is why I have a job, because their stuff is not as helpful. So this is the height, the sum of the log heights across my sample. Here's my scaling factor for how far off my data are from multivariate normal, 1.4. It's not 1, meaning that you should be using robust ML instead of regular flavor ML. Here's H1. This is my perfect model height. This is the height if I just let all the variances, means, and covariances be estimated. The log likelihood value for HO gets transformed into these additional metrics, AIC and BIC, and yes, if you know these from multi-level, these are the same thing. They are indices that are relative to each other, so again, the absolute values mean nothing, but you can compare these values for your model versus an alternative model. Smaller is better. There are no significance tests. You just have to say smaller is better. Chi-square test of model fit. So this is the difference in -2 log likelihood. So it's the likelihoods get multiplied by -2 to make their difference follow a chi-square distribution. So I'm trying really hard to say likelihood, but it's almost always -2 log likelihood because that's what the test is. So you have to take the likelihoods that are given and multiply them by -2. That's what the spreadsheet does for you. So this 307 is a scaled difference between the HO number and the H1 number for your likelihoods. The 9 is the number of degrees of freedom left over. So we had 27 pieces of data. We estimated 18 parameters with them. We have 9 left over. So we could add 9 things to our model before it becomes just identified. P-value being significant is bad. It means we did not get close to our saturated model. It is significantly worse than perfect. And here's the note that shows up in the output. I'm guessing a lot of other people screwed up their very first use of these chi-squares too, and so they feel compelled to give you this disclaimer. Question?
So this value is log scaled, sorry, the chi-square value is given as scaled in log likelihood or -2 log likelihood?
It is -2 times the difference in scaled log likelihoods. Yeah, I have to say it that way because if you just take the difference between this number and this number, it's not 309. So that calculation is done in the spreadsheet here. Or 307, excuse me. So the difference, the raw difference between those two numbers in log likelihood is 427. they calculate a difference scaling correction, and then they divide the actual difference by that difference in scaling. So again, to use this spreadsheet to do your model comparisons, folks, input the HO log likelihood, the scale factor, and the number of parameters, and the rest of this is calculated for you. So then on the next, after this disclaimer, I show you the math as to where those numbers came from that are in the spreadsheet. And I will prove to you that the model is saturated by showing you what it would look like to estimate it. So this is an FYI, folks. If you wanted to estimate the best possible model, the saturated model, this is what the code would look like to do it. So we have all possible means, because we have no factor anymore. All we have is data. Means in the first line, variances in the second line, and then covariances. And here's something I wish I had learned sooner. There's a shortcut. When you list all of the items, the keyword is with, which means covaried with, and then list all of the items again. That gives you all possible combinations. Otherwise, you would have to write 15 separate statements to get all possible covariances. So if we fit that model, then you'll see on the next page that the value given for HO and the value given for H1 matches exactly, because this is the saturated model. So you don't have to fit this. This is just for demonstrative purposes. But you'll notice the chi-square then is perfect, because there is no difference between my model and the saturated model, because my model is the saturated model. So now back to the model that we were working with before, the one factor. Here are the other indices of fit. So RMSEA, that one has error in it. We want it small. We want it to be less than 0.05 or 0.08, somewhere in there, and it's 0.17. So no, that's not good. The p-value on the third line there is significant, which means that the RMSEA of 0.17 is significantly greater than the RMSEA of 0.05, test of close fit. Next up is confirmatory fit index. The word fit means you want this to be big. CFI, the best possible, is 1. So we're only at 0.7, so that's not good. Same thing with TLI. It goes above 1, actually. It's even more unhappy with us. And then SRMR, residual. So that means we want it to be small. We want that to be less than 0.08. And so this one is relatively happier with us than everything else. So RMSEA and chi-square are relative to the perfect saturated model. CFI and TLI are relative to the null model. That means that one of these indices may like your model and the other one doesn't. They can totally disagree, and it happens all the time. The articles that I gave you also shed light on to when that can happen as well. Last but not least, the chi-square test of fit for the baseline model. This is null versus saturated, so this same number will show up anytime you use these data. It's the test of whether you have anything to model in the first place. It better be significant or game over. Then I work out the math for you to show you where that number comes from. And last but not least, here's what the code would look like to fit the independence model. So this is the worst possible model for comparison. Each item still gets its own intercept and its own variance, mean and its own variance, But note I've shut off the covariances. The second line after the with is at 0 for every single one of them, meaning all the covariances are held to 0. So then we have the HO model is the null model, and the chi-square test of model fit is 1128, which is the same thing that it is down here. Now, why would you ever do this? This provides an upper bound for just how bad your other fit indices can be. So CFI and TLI, those ones are relative to the null model, which is why they're 0. But RMSEA is relative to the saturated model. So this is the worst possible RMSEA you could have for these data. That's the upper limit, 0.26. Our model was 0.17, so that tells us we're not doing very well at all. All right, that's it. Any questions before we break? Alrighty then, office hours start now. Let me know if you need anything, otherwise I'll see you next Monday.